today we're going to be talking about something called subspaces. Here's the definition. So you have V, a vector space, and this is the abstract vector space that we talked about last time, not Euclidean space. If you have W, some subset of V, and if that W with the vector addition and scalar multiplication inherited from V, if that W with the vector addition and scalar multiplication inherited from V is itself a vector space, then we call it a subspace. Okay. So it's basically, a vector space that sits inside your vector space. Right? You have your big vector space, and then you have some vector space sitting inside of it. This is called a subspace. Okay. So just to give some examples. First, you remember we talked about the continuous functions being a vector space, right? Continuous functions on AB. If we look at the say the n times differentiable functions, right? So this is n times differentiable functions. N times differentiable functions on AB. Well, that's a subspace of the big space, right? With the with the addition, with the function addition, and with the scalar multiplication, this thing is a proper subspace of C. And the main thing that you need to see is that if you take one of these guys and you add it to one of these guys, do you stay in the space, right? If it's n times differentiable and you add onto it another n times differentiable function, is the thing still in the space? Is the result still n times differentiable? Yeah, sure, right? So so this thing turns out to be a subspace of that. Another example, if we consider the polynomials of degree less than n, which have a value of 0 at 0. So all the polynomials of degree less than n, which give you a 0 at 0. Okay. Is that a subspace? Is that a subspace? Well, are you able to add things together and still stay in the space? Right. If you take a polynomial which gives you a 0 there, and you add it to another polynomial that gives you a 0 there, will the result give you a 0 there at 0? Sure, right? Do all the vector space axioms still hold? Yeah, they still hold. Okay, so it turns out that this is also a subspace. So let me just give you sort of how the main thing that one needs to do is check the addition and the scalar multiplication. So let me tell you how it works. So basically, any non-empty subset W. So V is a vector space. V a vector space. Is a subspace if and only if W is closed under addition and scalar multiplication. Okay, so if somebody gives you some subset of a vector space and says, is this a subspace? All you have to do is check. If I add things together in there, do I stay there? And if I multiply by scalars, do I stay in that subset? And if those two things happen, then you can say, okay, yeah, then I have a subspace. Okay. So, right. So, for example, coming back here, if I said the polynomials of degree less than or equal to n, which take on a value of 1 at 0, would that be a subspace?
No.
No, why not?
Because you did like some addition or scalar multiplication, you got something different.
Right. So if you took two of these guys and you added them together, you would leave the space, right? Because the sum guy at 0 would give you 2. Right? If you took P1 and P2 and added them together, right? Suppose you got two guys in this space, P1 and P2. Right? Each of them takes on a value of 1 and 0. So when you sum them together, the sum is going to take in a value of 2 at 0. Right? So the sum, it's not. So this set is what we say not closed under addition. Not closed under addition, and in fact, it's not closed under scalar multiplication either. Because if you multiply somebody in here by 2, well, you've left the space again. So this is not closed under addition, and it's not closed under scalar multiplication either. Okay. If I said, let's look at the functions. This twice differentiable functions on AB where f prime and f double prime sum to 0. Is that a subspace? You're looking at twice differentiable functions that satisfy this differential equation. Okay. The derivative plus the second derivative is 0. Is that a subspace? Well, if you take two functions and you add them together, if you take two functions in this space and you add them together, do they still stay in the space? If you have one function, f, and you know that f prime plus f double prime is 0, and you have another function g, and you know that g prime plus g double prime is 0, is it true that the sum also lies in the space? Sure, right? Sure. You just, the derivative of the sum turns out to be the sum of the derivatives, right? The second derivative of the sum turns out to be the sum of the second derivatives. And so this thing here on the left turns out to be the sum of these left sides, which was 0 plus 0. Right? Okay. Similarly, right, is it true that if you multiply the guy by some scalar, does it still stay within the space? Sure, right? If you take the derivative of alpha f, that's just going to be alpha times the derivative of f, right? So this will turn into alpha times 0, which is 0. Right? Okay, so the solution set for this homogeneous differential equation is a subspace. More simply, maybe I should have started with the more simple stuff. Right? If I take, say, a plane going through the origin in R3, is that a subspace? So just remember, you need to check, is it closed under addition? Right? If I take two vectors in the plane, do I stay within the plane if I add them?
Yeah.
Sure. Right? If I take a vector in the plane and I scale it by some number, does it stay within the plane? Sure. So this is a subspace. Right? Okay. what if I took something like this? The upper half plane of R2, is that a subspace? Well, if I take two guys within the upper half plane and I add them together, am I still within the upper half plane? Sure. It's closed under addition, but if I multiply by a scalar, do I stay within the upper half plane? Not necessarily. If I multiply by a negative scalar, I leave it. Right? So this is not a subspace. Okay. Similarly, if I had something like this, right? I'm sorry. If I had something like this, is this a subspace? Why not?
Well, if you had a vector in there, you could multiply by a negative number, get outside the space.
No, it looks like if I multiply by the vector, I'm still going to be multiply a negative number. I'm still in my space. My space is the top and bottom. This and this together. So it looks like it's closed under scalar multiplication.
But if you add two vectors, it could be outside the shadow.
Yeah. So if I add somebody up here and somebody down here, I could get somebody pointing out this way, right? I'm sorry. I could get something like this. Right. So it's not. This thing is closed under scalar multiplication, but not closed under vector addition. Henry.
Can you go over the first two again?
This one?
Yeah.
Yeah, okay. So this one, if I take two vectors and I add them together, right? Well, I get a vector that's still in the upper half plane.
Yeah.
It's closed under vector addition. Addition is okay, right? But if I multiply one of these guys by -1, say, I end up with a vector that's outside the set.
Yeah.
So it's not closed under scalar multiplication. This one is the opposite. If I multiply by numbers, it's okay, right? If I take some vector and I scale it, I'm still within the set. If I scale it by a negative number, I'm still within the set, right? Closed under scalar multiplication. But if I take, say, this vector and add them together, right? Then I end up with a vector outside, right? I end up with a vector outside. So it's not closed under scalar vector addition.
And then what about the one on that one?
This one.
That one, is that subspace then?
This one is a subspace. So this is a plane. So you've got some plane in R3, and the plane goes through the origin.
Okay.
Okay. The plane goes through the origin. So if the plane didn't go through the origin, then you'd be in trouble, actually. Yes.
So are we assuming that any vector within a space, so before we actually talk about addition and scalar multiplication, we just assume that any vector within that space, right, or that subspace, we assume that we're talking about some vector within that subspace.
Could you say it one more time? I'm not. I'm sorry.
Yeah. So like if you look at the first one that you drew.
Yes.
So the two vectors that you drew.
Yes.
That is within the subspace.
Yes.
So do we assume that every time?
Well, if you're checking closure under addition, yeah.
Oh, okay.
So closure under addition means that, this theorem says to check it as a subspace, what you need to do is check if the subset is closed under addition and closed under scalar multiplication.
Okay.
So closed under addition means that, i.e., given any W1, W2, and W, the sum is still in W. Scalar multiplication means that given any closed under scalar multiplication means that given any W in W and alpha in R, then alpha W lies in W. I'm not gonna prove this theorem. The proof is boring. So I'm just gonna state it. Okay. But I hope you're all getting a sense of like what a subspace is and how to check if something is a subspace. Okay. Let me give you an exercise. So here it is. Yes.
I just had a quick
Yes.
clarification question.
Yes.
Sorry to go back to this, but so you're checking that the vectors in that plane are a subspace of that plane, or that?
I'm checking that that plane is a subspace.
Okay.
And to do so, one has to check that the plane is closed under vector addition. So that is, if you take two vectors in the plane and add them, you still stay within the plane. And you also need to check that the plane is closed under scalar multiplication. That is, if you take something in the plane and scale it, you stay within the plane. And as long as those things, as long as P is closed under addition and scalar multiplication, you know that P is a subspace. In fact, this is often taken as the definition of subspace. Okay. Okay, so let's do this. So this is not the exercise I was going to give, but we're gonna let me define something. Okay, so you have some matrix, an m by n matrix. We define the null space of A. It's denoted n of A by n of A is all the vectors in Rn such that Ax is 0. Okay, so the question is N a subspace? So think about that for half a minute or a minute, and then tell me if it is or not. Okay, talk to somebody next to you. Talk to somebody nearby about this question.
It's just one vector. It's where it is. Yeah, so all of the vectors, I guess we must just add to 0. He specified because we're
Yes, like any. But I don't think you have. I don't think it's necessary.
Okay,
It's not at 0.
that could be like one.
Yeah. Because if you have,
Are we on the right track?
I'm not listening.
Alpha by Ax.
Is the null space just one vector?
No, it's all vectors that get killed by the matrix, right?
so if
All x in R such that Ax is the 0 vector. Everything that this matrix sends to the
you
0.
have two, you have x
I feel like
and
it's
y, and x plus y, that's the times where the matrix, where it's like, but that can be like.
For example, if A were the 0 matrix, then the null space would be everything, right? Because the 0 matrix would then send everything to 0. Okay, what do people say? Is it a subspace? Is Is it a subspace? Well, what do you need to show? What would you need to show? You need to show that if you have two guys, right, you need to show closure under addition and closure under scalar multiplication. Right? So is it closed under addition? Suppose you have two vectors right? If V and W are in N and A, is V plus W? Is V plus W in NA in the null space? If you have two guys in the null space, is there some in the null space? Okay. Zane is nodding. Andrew's nodding. Right? Why? Well, right, if you've got somebody in the null space, it means you get killed by the matrix. Sends you to 0. Right? Right. So you know that right. AV is equal to 0 and AW is equal to 0. Does that imply that A times V plus W equals 0 is the 0 vector? Well, certainly, right? Because A of V plus W is AV plus AW, which is 0 plus 0, which is 0. Right? Okay. So the null space is closed under addition, right? Second part, right? If V is in the null space, is alpha V in the null space? Right? If you take somebody that gets killed by the matrix, is it true that any scaling of it will be killed by the matrix? Yes, you all should be more confident about this, right? Sure, right? A of alpha V is the same thing as alpha AV, right? V is in the null space, so this is A times 0 matrix, 0 vector, so you get the 0 vector. I guess this is the sickness that happens to people when they first start encountering theoretical math, because now they're like, I don't know, I don't know. Right? I had to show that 0 times something was the 0 vector. I'm not sure of anything anymore. So this is the sort of, yeah. But don't make it harder than it is. Don't make it harder than it is. Right? Right? Just think, what are they asking? Right? Is this thing a subspace? What does that mean? It means that we need to show that if you have closure under addition, that is, if two guys are in the subspace, is there some in the subspace? Yeah, it is. Right? If two guys get killed by the matrix, will there some get killed by the matrix? Yes. If one guy gets killed by the matrix, will its scaling get killed by the matrix? Yes. Right? Because of distribution, and because of associativity. Or commutativity, sorry. Of scalar multiplication. Okay, so this is an example of a naturally occurring subspace. Subspaces. So this will be pretty important, the null space. Null space, also sometimes called the kernel. Kernel, K-E-R-N-A-L. Okay. We're going to do something very concrete now. Something very concrete and familiar to you. Right? Finding the null space of a matrix. It's like we're going back into the concrete world of numbers. So you have some matrix and I'm going to write this down, but I'm going to immediately erase it, so don't worry. 1, -2, 1, -1, 2, -3, 4, -3, 3, -5, 5, -4, -1, 1, -3, 2. I guess I'm not immediately going to erase it, but I'm going to immediately ignore it. So this reduces to 1, 0, 5, -3, 0, 1, 2, -1. Okay. So, as this is all stuff you've seen before, basically. So, right, you got this thing, x1 plus 5x3 minus 3x4 equals 0. X2 plus 2x3 minus x4 equals 0. Right? If you're considering the null space, right? You want to find x1, 2, 3, 4 such that the product is 0. Right? And so you end up with this system of equations. Okay? Just as you did before. Okay? So that is any solution of ax is 0 must be of the form right, -5x3 plus 3x4 -2x3 plus x4 x3 x4. Which we can write as x3 times -5, -2, 1, 0, plus x4 times 3, 1, 0, 1. Okay, and so this allows us to describe the null space, right? So the null space of A we can write as the span of these two vectors, right? -5, -2, 1, 0, and 3, 1, 0, 1. The span. This is a little bit imprecise. I should say all solutions the solutions are all vectors of the form blah, where x3 and x4 are. You've seen this sort of thing before, right? Finding the solution set to some homogeneous problem, right? All we're saying now is just that what we were doing before was finding null spaces. Okay. Okay. Do you all remember what the span is? Do I need to redefine span, or do you all remember? You don't remember? Okay, let me redefine. Okay, so recall, we had a couple of definitions early on. One was linear combinations. So you start off with some vectors, v1 through n, in some vector space. Some vectors in a vector space, any vector of the form alpha 1 v1 plus alpha 2 v2 plus alpha n vn is called a linear combination linear combination of V1 through Vn. Okay, linear combination. 2, the span of V1 through Vn is the collection of all linear combinations of V1 through Vn. Yeah, Leah.
I'm sorry, I didn't hear. What does the VS mean?
Vector space, sorry.
Okay.
So you have some vectors in V, a vector space.
Okay.
Okay. So the span is just a collection of all linear combinations. Right. So here we saw that the null space was all linear combinations of these two vectors. In other words, the span of these two vectors. Right. It's any multiple of the first guy plus any multiple of the second guy. Okay. So here is a maybe simple theorem. Any span is a subspace. So is that obvious? If you take a bunch of vectors and then look at their span, is that going to be a subspace? Well, the only thing you have to do is check closure under addition and closure under scalar multiplication, right? So if you're looking at a span, you take two guys and you add them together. Is that still in the span? Sure, right? Because any linear combination plus another linear combination is just going to be a linear combination, right? The span is all linear combinations. So if you take one linear combination and another linear combination, you get a linear combination. So it's closed under addition, right? Is it closed under scaling? If you take a linear combination and scale it, do you still get a linear combination? Sure, right? So this is sort of trivial. This is really an exercise rather than a theorem. The span of any span is a subspace. Okay. Let's see. Okay. Another exercise. Suppose I give you. This is problem 13 from your homework. Suppose I give you one vector, -1, 2, 3, and I give you another vector, 3, 4, 2. And I give you some vector b, and b is called 2, 6, 6. Okay. And I ask, is b in the span of u and v? Okay. Is b in the span of u, v? See if you can answer this. This is sort of like a review of stuff you did before. So you take 1 minute, take 2 minutes and see if you can answer if B is in the span of these two guys. Okay, so what do you do? How do you answer the question? Teresa?
Check closure in addition and closure in scalar multiplication.
That would be to answer the question, is this a subspace?
Oh, okay.
So that's a little bit different question. Rather, we're asking, is this B? Can this B be expressed as a combination of these two guys, right? And that's something you actually can figure out in a very concrete way, right? How do you do it?
Yeah.
Right? So you say, well, right, we want to know, can we express 266 as some number times the first guy plus some other number times the second guy? Right? Right? But that sort of question we've answered many times before, right? What question is that?
Will equivalent.
What? Yep.
Will equivalent.
It's the sort of.
Not even close.
You're close. You're close.
Just an
You're not completely wrong.
just an equation in two variables.
Yeah. Right. This is just your equation.
It's like
Right?
ballpark.
You're solving.
Ballpark. Something like that.
Right. This is the question you're solving. Right. Right. This is the question you're solving. Right. It's equivalent to this. Right. Okay. Right. This question is the same thing as this question, right? And so it's a question about, taking this matrix and seeing if it has any solutions. Right? And so this is something you know how to do. We're not going to do it. Okay. The main thing is that I hope you remember. I hope you understand that this question is the same thing as that question. Right? The same as the questions we've seen before. Okay. So just remember the connection between this sort of question and that sort of question. Okay. Another question, another exercise for you, number 19. Why is it true that that the null space is 0 if and only if A is invertible? Why is it true that the null space is the 0 element if and only if A is invertible? This again is sort of a review question. In fact, it appears that most of the rest of the lecture is review questions. Mia, do you know?
Is it, if it wasn't invertible, it wouldn't pass scalar multiplications?
If it wasn't invertible, so the question is this, right? That the assertion is this, that the null
Never mind.
space.
Never mind.
Okay, that the null space is the 0 is 0, if and only if the matrix is invertible. The null space, so I think people are sort of getting bogged down by language, right? The null space is the things that get killed by the matrix. Okay? The null space is the space of everything that the matrix sends to the zero vector. Notice that the 0 vector is always in the null space, right? Because if you hit the 0 vector with anything, it gives you the 0 vector, right? So this is saying that the null space is only the 0 vector, the 0 vector and nothing more than the 0 vector, if and only if the matrix is invertible. Okay. So this is sort of like a test of your memory, I'm afraid. Do you remember we had this theorem that was talking about invertibility, right? Like invertibility is equivalent to this, equivalent to this, equivalent to this, right? Can people tell me like a couple of those things? Like what was invertibility equivalent to?
A of x has a unique solution. A of x equal to the zero vector.
Yeah,
Unique
yeah.
solution.
Ax equals 0 has a unique solution, namely the zero vector. Right. That was equivalent to invertibility. Okay, so
Wait, sorry, why is that equivalent to invertibility?
do you remember we had this long list, and we proved this implies that implies this implies that, and went all the way around again. Yeah. So this was one of them, and so yeah.
But does the null space have to equal 0 because that's the only solution Ax equals 0 has?
Yeah. So this statement that the null space is equal to 0 is basically exactly this statement, right? It's the same statement. The null space is 0. The only thing that gets sent to the zero vector is 0, right? Okay, so it's almost just a matter of checking if you understand the language. Okay, right? For the null space to be 0 means that the only thing that gets sent to 0 is the zero vector. That is, the only solution to this equation is the zero vector. Okay. So this is trivial if you understand the language. You just say that's what the theorem says. Okay. Yeah, sorry, it's maybe not the most exciting stuff. Next time, I promise it will be more interesting. We'll talk about something called linear independence, which always boggles everybody. Yeah. So this time, you see, this time it's sort of maybe not the most interesting stuff. Let me. So let me give you another sort of similar question. So somebody asks you, is the span of 1, 0, 1, 1, 1, 0, and 0, negative 1, negative 1, all of space, all of R3? Is the span of these three guys. So somebody gives you three vectors in space and says, do these guys span the whole space? Do these guys span all of space? Okay. So this is just, again, sort of a translation problem, right? Right. The question is, so rephrasing. The question is, given any ABC in space, can we find x1, x2, x3 so that x1 times the first guy plus x2 times the second guy plus x3 times the third guy equals ABC. Right? That's what span means, right? Can we realize anybody in space as a linear combination of these guys? Right? And so again, this boils down to solving. Right? So this is equivalent to, can we solve 1, 0, negative 1, 1, 1, 0, 0, negative 1, negative 1, A, B, C. Right? Can we always solve this system? Okay. And so you do your Gaussian reduction on this thing, right? You do your Gaussian reduction, blah blah blah, and you end up with something like this: 1, 1, 0, A, 0, 1, negative 1, B, 0, 0, 0, C minus A plus B. Okay. If you do your Gaussian reduction, that's what happens. Okay. And so what's the answer? The answer is no, right? The answer is no, you can't always solve this. You could, as long as C minus A plus B is 0, then you're okay, right? So if C minus A plus B equals 0, then you can solve, right? But if it's not equal to 0, then this is impossible. Okay, and so the answer is no. The span isn't all of R3. It's a plane. It's actually this plane, right? Z minus x plus y equals 0. Right, so the span is actually